Hello everyone. I wanted to take an opportunity to dive in a little deeper with aromatic compounds from our chapter 13. It begins in section 9 with just introducing the type of compound known as aromatic compounds and specifically focusing our attention on a compound known as benzene. Benzene is a very important solvent used in the organic lab, and it is worth getting familiar with the term benzene and all of its derivatives. Notice that it has a formula of 6 carbons and 6 hydrogens that are in a cyclic ring where you notice that we are alternating a double bond, single bond, double bond, single, double, single, all the way around that cyclic structure. Going from this molecular representation to a line drawing, we can see that the carbon backbone has been shown with this ring structure, and we're alternating double, single as we move around. And again, we can see that this is a very planar molecule with the ball and stick model. Using these carbon atoms, we can see that their bond angle is 120 degrees, suggesting that we have sp2 hybridization. For molecular geometry, it's a very flat molecule. So the geometry of trigonal planar allows us to see that it's a flat molecule that lies flat on the table. Trigonal planar, 120 bond angles. And let's dive a little deeper into that definition of what it means to be an aromatic compound. Notice that we have a single bond in one structure and then a double bond in the next structure. So double, single, as we had mentioned in the previous slide. That same arrangement of atoms but different location is key in understanding a delocalized electron. And I want to emphasize delocalized so that let's just label this carbon as we move around the ring. We'll just randomly pick a first carbon and move around counterclockwise and number it 1 through 6. Between carbon 1 and carbon 2 is a double bond. And if I'm just emphasizing that we're not shifting, we're not just simply rotating the molecule in space, but I'm leaving the carbons in the exact same area, and I notice that the double bonds have actually moved. Instead of the original carbon 1 and 2, and the next slide over, they're looking at between carbon 2 to 3, and now carbon 4 to 5, and carbon 6 back to 1. I realize that we should always start numbering at the double bond, but we're emphasizing with a structure that has delocalized electrons that those electrons are not necessarily in a position between two atoms of carbon at any one time, but rather evenly distributed around the entire ring. So a delocalized electron does not spend its time specifically between just 2 carbons, but rather between all carbons to create an equal distribution of electrons. So evenly distributed around the entire ring. So instead of thinking of them being localized, which is just between 2 atoms at one time, they are delocalized, spending time between all atoms in an even distribution. Any structure that does this exhibits resonance. And what we're learning is that this truly is not a representation that we find in a moment of time. It's not like this structure exists for a moment and then it turns into this structure in the next moment, but it's a hybrid of both structures at the same time. And you'll often see a chemist draw those delocalized electrons simply by saying it's not really double, single around any particular point, but a delocalized ring, saying that those electrons are actually all places at once. So that's what we're referring to with an aromatic compound, such as benzene, that exhibits resonance, that they have delocalized electrons free to move around the ring in an equal distribution. And we're learning that that is an incredibly stable configuration. So those delocalized electrons are in any compound that exhibits resonance. And the term resonance means that I can simply draw more than one correct structure for a particular Lewis dot structure. Let me just take a moment and emphasize the term resonance. Let's take a quick peek at a polyatomic ion called carbonate. Carbonate is CO3 and it carries a -2 charge. When we draw the polyatomic ion structure for carbonate, we end up drawing a structure that looks like this. The -2 charge comes from the formal charge on each of those oxygens. Carbon is obeying the octet rule with 8 electrons in the shared pairs. So one possible structure for carbonate shows that the double bond is between the carbon and this particular oxygen in that structure, but an equal valid structure for the carbonate ion could show that the oxygen double bond goes to a different oxygen. And friends, it's not just by spinning it in space, it's by actually breaking this bond and moving it down here. And there's a third equal structure that I could create, and that's to point down at the double bond and form a third resonance structure. Carbonate has 3 equivalent structures I can draw. Those structures are known as resonance structures, and the truth of the matter is one of them is not any more accurate than the other. One of them does not exist for a moment of time and then the other and then the third. They exist equally in a blended delocalized way, and often you'll see a delocalized electron bond really is just drawn as a slash and these little dots here saying not really a true formed bond, but a delocalized bond, meaning the electrons spend time evenly distributed between the carbon and all 3 oxygens. They have an equal bond length. So if I stand at carbon and I look out in all directions, the oxygens are of equal distance from the carbon. Whereas if I come back and I look here, if I stand at carbon, I might think this oxygen is closer because of the double bond as compared to the longer single bonds. I might think that this oxygen is closer than these longer bonds here, but they're not. They are of equal distance, verifying that these structures are indeed a hybrid of all true structures together. So they don't exist except on paper. And that's really what the story is then about benzene, C6H6. These structures are known as resonance structures, but the truth is that it's a blend or a hybrid structure of both of these at any one point in time. So benzene is very different than a true double bond. Notice that this is an alkene. It has a double bond, and we just spent time practicing how alkenes undergo all types of addition reactions. With addition reactions, we added hydrogen across the double bond. We added a halogen across the double bond. We even added a halogen and a, let's do that. I'll put HX representing hydrogen halogen, and H to one side and the halogen to the other. And we even practiced with HOH, the hydration. All of these are addition reactions to an alkene. But now I'm saying this benzene is not an alkene. In other words, it's not a true double bond. It exhibits resonance. So because it's delocalized, these do not behave like double bonds, and you do not see any reaction with a benzene ring as we did with a true alkene for an addition reaction. Now in a moment, when we get that far, it will undergo substitution, and we'll practice those, but no to addition. There are no addition reactions for benzene because they are not true double bonds, but we are allowed to do a substitution reactions just as the alkane family also performed, and that was from chapter 12. Let's spend a moment talking about nomenclature of the benzene derivatives. With our benzene derivative, I want to make sure you're hearing. With our benzene derivatives, we're going to practice naming some different types of aromatic compounds with a base root of benzene. So very similar rules to the IUPAC that we've been practicing before. When we're naming a benzene ring with a substituent, we label the substituent in alphabetical order. Here we have 2 carbons off of a benzene ring. That 2 carbon has a root word ethyl. Notice the YL telling me it's a substituent group. So we name that simply as saying ethylbenzene, all one word. Here we have a branch coming off a benzene that is 4 carbons long. We'll call that a butyl group. Notice the YL ending tell me it's a substituent off of a benzene. It's simply called butylbenzene. And here we have chlorobenzene. And any halogen that we were to connect off of a benzene ring, this would simply be called iodobenzene. Notice how it ended in O. So those halogens are also named alphabetically if we do have more than one on the same ring. We have some common names for some monosubstituted benzenes that we need to memorize because they become root words when we name. For instance, if I see a methyl group off of the benzene ring, it is not okay to name that as methylbenzene according to IUPAC. Instead, this becomes the root word. We have to call this toluene. If I see a hydroxyl group coming off the benzene, we need to call that phenol, and we're going to practice that alcohol ending. The alcohols will end with OL, phenol. And here we have aniline, A-N-I-L-I-N-E. I hear it called aniline, and I hear it called aniline. I think that's your preference, but it's this amine group coming off of the benzene ring. So this is our structure where we have NH2, and remember there's a lone pair there. So we have our connection here to the benzene ring, and we have that amine group with 2 hydrogens coming off. So aniline, phenol, and toluene, we should remember those when we're practicing naming our aromatic compounds. Oftentimes, instead of using numbers, 1-2 or 1,2, 1,3 or 1,4, what you'll see instead are prefixes that we will denote those positions as. Here I have an ethyl group in position 1 and position 2 on a benzene ring. You may say that as 1,2-diethylbenzene. In position 1 and 2, there is a group of ethyl, so the di tells me there's 2 of them on a benzene ring. However, more often you're going to hear a prefix for that position called ortho, and we shorten that to be O. Ortho-diethylbenzene is how I still read that. Even if I see an O, I hear myself saying ortho. 1,2-diethylbenzene is also known as the ortho position 1,2. If we see substituent groups at position 1,3 on our 6-carbon ring, that gets the prefix meta. 1,3-diethylbenzene is also known as meta-diethylbenzene. And here we see the position is 1,4. The position 1,4 is known as para-diethylbenzene. We'll see that written with just a P, but it means to me the position is 1,4-diethylbenzene. Ortho, meta, para gets abbreviated with O, M, or P, and when I see those abbreviations, I understand they're telling me the locations of the substituent groups. So here's a set of examples to help emphasize the ortho, meta, para positions. Here's my 6-carbon ring of a benzene. I notice it's benzene because I see the alternating double, single, double, single, double, single all the way around the bond. So the ortho position puts bromo in position 1 because of the alphabetical position, and chloro would get position 2. I name that, I could say 1 bromo, 2 chloro, benzene, but more often, more common, you will just hear that written or seen it written here. It said as ortho bromochlorobenzene. This ortho automatically tells me the positions in alphabetical order of the substituent groups. Notice here you have the position of 1, 3. Going by the alphabet first, position 1 gives priority to the ethyl group. Position 3 gets fluoro. Based on the alphabet, meta-ethylfluorobenzene is 1 ethyl, 3 fluorobenzene, which is correct. It's just that you hear more often the meta position. So practicing some of those allows us to keep emphasizing those words that we're working for other backbones, such as toluene and phenol and nitrile. We're looking at memorizing those groups. Here's my benzene ring with this methyl after it. So here's a methyl group. One way of naming that you might be tempted is to call this, if this is a methyl, and going by alphabet, you might want to call this 1 bromo, 4 methyl benzene. But in your head you go, wait, that's one of these that I had to memorize as having a different backbone name. We have to remember that a methyl benzene has to be labeled as a toluene. So when I call this para-bromo-toluene, I understand that toluene is the methyl benzene. The para position is also denoted with the 1,4 position. Here I have a benzene ring with the hydroxyl group and a chlorine group. So here is the chloro, and here we would label this hydroxyl, except we're working to memorize that this, instead of saying hydroxyl benzene, I have to recognize that that's a backbone we have to memorize as phenol. So with phenol, this was the ortho position, and the ortho position is 1, 2. We would call that orthochlorophenol. So those that we just backing up, these slides here, we have to recognize these as backbone names, and if I place something else on that as a substituent, I label that then with the aniline backbone name. So for instance, this would be meta-chloro-aniline, position 1, 3. And it will become familiar as we begin more and more practices. And just some other reminders with your nomenclature: always give the lowest possible numbers around the ring. Remember to alphabetize your substituent names and work with those substituents as part of those common roots. So the derivative of benzenes that you're looking to remember, coming back here, toluene, phenol, and aniline. Some people call it aniline, your choice. I think either is appropriately correct. Remember that the derivative is the root word, so therefore it's given the position 1, but we don't need the 1 in the name. We'll automatically know that that's the position of carbon. So what they're saying is, if this is our benzene ring and we have a OH group there, we know that the OH group, because we're working to memorize, is called phenol. And so if I were to have the backbone here called phenol, whatever I put on this side, this gets priority as carbon 1. So 2, 3, 4, labeling this as 4-chlorophenol. Better than that would just be simply saying para-chlorophenol, because we know carbon 1 is going to be the hydroxyl group because it is part of the backbone name. If we have a polysubstituted benzene, we just think about alphabetizing and making sure the numbers are in the lowest position possible. Here I have an ethyl group. Here is a propyl group, and here is a chloro group. Beginning with the alphabet, we may be tempted to call chloro in position 1, but that would put this at carbon position 3 and 4. If I numbered in a counterclockwise way, I would have the substituent groups as at position 1, 3, 4. But notice if I label this as carbon 1 and I continue to number around the ring, I have them positioned at 1, 2, 4. And that, of course, is a lower numbering system. And then we alphabetize. Chloro comes first at position 4. The ethyl comes next in the alphabet at position 1. And then finally position 2 with its propyl. That's 4 chloro, 1 ethyl, 2 propyl benzene. And notice with 3 substituents, the ortho, meta, para do not work. They only work with 2 substituents. Here we have a position, just as another practice. Notice that in shaded here is the aniline or aniline. Shaded here is the backbone word, and so automatically that's given carbon 1. I want to find the position then that gives me the lowest numbers possible on the substituent group, and that becomes at position 2 is the chloro, and at position 5 is a chloro, so we have a dichloro name. 2, 5 dichloroaniline. Position 1 always comes from the backbone root word name. We'll also discuss in depth here now the common reactions that we see of an aromatic compound. Remember that aromatic compounds undergo the same type of reactions as alkanes, which are the saturated compounds, all single bonds in chapter 12, the alkanes, and those are known as substitution reactions. Just to emphasize, we practiced in this chapter alkene reactions, which were addition reactions. So let's make sure we see the difference. These are substitution. I'm going to just add that word right to this slide. Let's model the difference between a substitution and an addition. Here we have a reactant. The reactant here is benzene, C6H6. And notice that this structure would actually have equal hydrogens all the way around. They're not shown, but we know that they're there. So there's the compound. There are 6 carbons in a ring, and coming off of those carbons, each has 1 hydrogen. Now, any of these hydrogens can undergo a substitution. So our reactant is a compound where any element X is hooked to any element Y. In this particular case, we're using general letters just to model the pattern. And in a substitution reaction, we take one of the hydrogens and the element written first in our compound, and we just exchange their places. When we exchange their places, we're substituting a different element onto the benzene ring. So at the position that used to be one of the hydrogens now results in this element we're calling X, and the hydrogen itself now is hooking to the other element from the reagent HY results. So a substitution, take one of the hydrogens off and exchange it with the element written first in our formula here. Now remember, addition reactions take a double bond and turn it into a single bond and adding all 4 bonds back to the carbon. That's what we focused with alkene. And we did addition reactions using hydrogen, using halogens, using a hydrohalogen, and we hydrated HOH. When we break a double bond and turn it all back into single bonds, we have addition reactions. Taking this compound and taking the double bond and breaking it and going back to an sp3 hybridization. There's none of that going on here. These are substitution reactions. Both alkanes and aromatics are allowed to do this type of chemistry. An exchanging of two atoms from the ring and halogenating or whatever it might be onto that benzene. So here's a specific example, just to emphasize again what a substitution reaction will do. There are 6 equal hydrogens on our benzene ring. We select just one of them and take the chlorine, which is in the first position here, in the presence of our catalyst, and we exchange places with the hydrogen and the chlorine, and we substitute the chlorine to the benzene ring. And we end up with a chlorobenzene and an HCl. Notice we're just exchanging places. Let me model one from your homework just to give you an idea. It's called halogenation of an aromatic compound. So when we think about aromatic compounds, we automatically know that this is discussing our benzene. So if I think about drawing a structure, when the product formed when paradichlorobenzene is treated with chlorine and iron chloride. Let's begin by taking these words and beginning to turn them into a structure. Paradichlorobenzene. I begin with my benzene structure, which I know alternates double single all the way around. And remember, it is absolutely just as valid to have put your double bonds in a different position. They can alternate double single in any way you begin. So these are equal. Alrighty, but just to kind of remind us that it doesn't matter, I'm going to focus with the one I drew first. This position para tells me that it's position 1,4. So at carbon number 1 and carbon number 4, I have 2 chlorines. This is how we read paradichlorobenzene. It says we're going to treat it with chlorine, Cl2. And I'm just going to remind me that 2 chlorines is actually bonded, 1 chlorine to the next with a single bond. And the catalyst is iron 3 chloride. So we just set that on the arrow. Remember that there's hydrogens, even though they're not drawn, we know that they're there. And we have 4 equivalent hydrogens. The equivalent hydrogens mean that I have 4 choices of a hydrogen to take off. Any of them are exactly the same. There's no difference in where they're located. So let's just select this hydrogen. And the very first chlorine, since it's in the first position, they simply exchange places. In our substitution reaction, where I originally had this hydrogen, I will now place the chlorine. Remember the 2 chlorine that were there before from the para position. And by the way, we would end up with the other product, HCl. So these 2 have exchanged places. I end up now with 1, 2, 4 trichlorobenzene. No longer does the ortho-meta para work because I don't have just 2 chlorines anymore. I have 3, so all must appear in the name. When we have an aromatic compound and it's treated with nitric acid, HNO3, in the presence of a catalyst, and this catalyst is called sulfuric acid, battery acid, we end up with a new functional group, and that new functional group is called nitro. The nitro group, NO2, comes from the treatment of HNO3. We end up with a substitution reaction in the following way. And take a look with me down here. I had drawn earlier the actual Lewis structure for nitric acid. Notice that we have nitrogen as the center atom. We have a double bond coming down to an oxygen. We have a single bond coming to the right, and it's carrying a negative charge, and it's going to this acid proton here, OH. So this is the valid Lewis structure for nitric acid. We're going to take two oxygens and the nitrogen. That's the functional group called nitro. See how that's NO2, nitro? And what's left is an OH that when it substitutes with the H, this is why we end up with water as the other product. The OH from the original acid will combine with the H that we're substituting the nitro with on the benzene ring. We end up with a nitrobenzene. The substituent group is NO2, nitrobenzene, and a water molecule, the H, and the remaining OH from the original acid ends up to make water. So when I come back here to this slide where I said, let's work to memorize these, it might be very helpful to add another one. And if you see this, you can add that to your vocabulary as being nitrobenzene, just to kind of keep in mind that NO2 functional group is worth remembering. So I drew a picture cleaner for us. When I create a bond, this is where it attaches to the benzene ring. Whoops, I spelled that wrong. So that's the site of attachment in the product. The benzene ring, when it finally attaches to this nitro, you end up forming a double bond to the oxygen, a single bond to that next oxygen, and it is actually a -1 formal charge. And notice that this nitrogen only has 1, 2, 3, 4 bonds, but no lone pair. There's no dots there. There's no lone pair of electrons, and that's why you see a positive charge, because it has an empty orbital. So you'll see the positive charge on the nitrogen, a negative charge on the oxygen, and the site of attachment here to the benzene ring. This is the detailed drawing of a nitro group. Putting that into practice, let's start with our paradichlorobenzene. Again, let's take a moment and draw what we're starting with. We have a para position of a benzene, and those are both chlorines, paradichlorobenzene. And we're going to treat that with nitric acid in the presence of our catalyst called sulfuric acid. Remember, a catalyst sits on the arrow. It is not a reactant, not a product, so it sits on the arrow. It improves the rate of the chemical change. And know that even though they're not drawn, we know that there are hydrogen on this benzene ring. And those 4 hydrogens are of equal worth, right? They're all equivalent hydrogens. So where I have a hydrogen, I could select any one of them. They'd all end up to be the same structure. I'll pick this guy. I'm going to substitute a nitro group. So when I see nitric acid, the substitution is a nitro group. And so when I begin drawing my product, let's change color. I go back to the original paradichlorobenzene. And instead of this hydrogen now, I have a nitro group. And the nitro group has a double bond to an oxygen that's carrying 2 lone pairs. It has a single bond to an oxygen that has 3 sets of lone pair electrons, and it carries a -1 charge. And because nitrogen has an empty set of orbitals, it has the positive charge sitting on it. So it only has 1, 2, 3, 4 assigned electrons carrying a formal charge of +1. Also, we have the OH as the other product, even though it's not asking me for that on this question. This doesn't just disappear. It takes an H and an O and an H to make the water as the second product. So here we would have a situation where we have our grouping with a nitro on it. Alrighty. So when I see substitution with a nitric acid, I add a nitro group on, leaving a water molecule in its path. And that's what we drew. Another practice with a benzene derivative, it asks us to draw the structure of TNT. That stands for trinitro-toluene, 2,4,6-trinitro-toluene. Well, I see the root word toluene. And are you working to memorize what those words stand for? Toluene. I'm sliding back up to say, here's that slide where I have to memorize what toluene is. Toluene is methylbenzene. So when I see toluene as the base of my root word here, I can begin drawing this with my 6 carbons, alternate double, single, and I have a methyl group. This part is the beginning of that structure when I see the name toluene. And now I can see that there's positions 2, 4, 6, knowing that that's a 1. That always gets the 1 because it's part of the base word. I spoke and wrote at the same time and ended up with a spelling error. Let me fix that. At position 1, 2, 3, 4, 5, 6, we have nitro groups. At position 2, position 4, and position 6 are nitro groups. 2, 4, 6 trinitro-toluene. That is the chemical breakdown of TNT. And if you wanted to draw each of those, and again, remember, it doesn't matter which way you point your 6-cycle structure, whatever you prefer. Here's your methyl group. You'd have position 1 where you'd have a nitrogen, single bond oxygen. It carries a -1 charge, nitrogen with its +1. And you could keep drawing those. One position with a double bond, one position with a single bond. It's negatively charged, positive on the nitrogen. And one more to draw. Making it negative and the nitrogen positive. Another view of the same structure with more detail. Trinitro-toluene, TNT. And again, I'm just working a couple homework problems, hopefully to help you out. We're going to ask to be given the structure and then just name it as well. So giving the name, draw it. Well, here's that root word, toluene. So when I think of the root word, we have to memorize toluene as being methylbenzene. So that's this word, toluene, drawn out. It gets position 1, and I'll just number this direction. I could go either way. At position 2 will be a bromo, and at position 4 will be a chloro. If I had numbered any different, it still comes out the same, just to kind of think that through. If I had started with 1, I would still have bromo here, chloro here, and I'm just twisting the molecule in space. Those are all equivalent structures. Ortho-iodo-phenol. Phenol. I'm working to memorize the phenol functional group. Remember here, phenol, it's the hydroxyl group on a benzene ring. So recognizing those helps me draw correct structures. So if I come back to this slide, I know that I'm beginning with a benzene ring. that has an alcohol group, OH. This is the root word, phenol. Ortho tells me it's position 1 and 2. I know that carbon 1 is on the alcohol because it's the root word phenol. So in position 2 would be the iodine, iodo. 1, 2, iodophenol. Ortho, iodophenol. So I hope this has helped you as you work to master your Chapter 13 lessons. I know you're working on your Connect homework due tonight since I'm making this video on Thursday morning. And I hope you found it helpful. Remember, tomorrow in class we're looking at some alcohol nomenclature and you'll prepare there.